Hello. We're doing section 12.3. So that's the last section that we're covering on chapter 12. That's about permutations and combinations. So this is an extension or an application of the fundamental counting principle. We will start first with permutations. So I'm copying the definition. And a permutation is an ordering of distinct objects. So in a permutation, order matters. A permutation is an ordering of distinct objects. If we select our different objects from a set of n objects and arrange them in order, this is called a permutation of n objects taken R at a time. The number of permutations of n objects taken R at a time is denoted by P of n, comma R. So this denotes the number of permutations of n objects taken R at a time. A good example of that was example 5 in one of the previous sections when we're doing the keypad patterns. Or maybe I can bring it back. So that was 12.2, I believe. Okay, so yeah, that's a fundamental counting principle. Yeah, the one with the keypad patterns. Yes. Let's find this. And I believe it was number 5. And there it is. So the last one, the last case, the last situation, we were forming different keypad patterns. So the last case, any digits can be used in any position, but repetition is not allowed. That's example of permutations. And by using the fundamental counting principle, so the order is important, but you cannot repeat any digits. So in this example, we found the total number of permutations. But I'm going to go over example 1 on section 12.3. And there it is. How many permutations? Oops, sorry about that. How many permutations are there of the letters A, B, C, and D? Write the answer using P of N R notation. So we have 4 letters, and we're looking for the number of permutations of 4 objects taken 4 at a time. So we're going to, that's A. We're going to find all the permutations, or not all the permutations. Find the number of permutations. Of 4 objects taken 4 at a time. The permutations themselves would be A, B, C, D is 1 permutation. A, B, D, C is another permutation. B, C, A, D is another permutation, and so on. Okay, so we're going to use the fundamental counting principle. So we can use slot diagrams. So initially, for the first box, we have 4 letters. Since we cannot repeat elements in a permutation, we have next 3 elements, then 2, then 1. And the product is going to be 24. Okay, so using the notation, we're looking for the number of permutations of 4 objects taken 4 at a time. So P of 4,4 is 24. Any B, how many permutations are there of the letters A, B, C, D, E, F, and G if we take the letters 3 at a time? Use the answer P, using P of N R notation. Okay, so here we have 7 letters. And we're looking for the number of permutations of this 7 letter if we take 3 at a time. So that's going to be notation, that's 7, P of 7, 3. Okay, so we have 3 spots. So using a slot diagram, first we have 7 choices for the first letter. Once we select the first letter, we have 6. And for the last letter, we have 5 choices left. 7 times 6, 42, times 5 is 210. So P of 7, 3 is 210. Okay, so well, you can see a pattern. We're using the fundamental counting principle, but if you want to write a formula, for the number of permutations, we need to talk about factorial notation. Or the factorial of a number. Okay, the notation is N with an exclamation mark. So that N exclamation, and this is N factorial. So if N is a counting number, the symbol N exclamation mark or N factorial stands for the product of N times N minus 1 times N minus 2 and so on and so forth up to 2 times 1. And we're going to define 0 factorial to be equal to 1. Okay, so we're going to do a few examples, a few exercises with factorial. So we're going to compute each of the following. Yeah, 0 factorial is going to be, well, there's a reason why this is equal to 1. And I can, yeah, I'm going to show you, you're going to see this in some of the following examples, why we need 0 factorial to be equal to 1. Okay, but let's start with 7 factorial. So 7 factorial is going to be the product of 7 and the preceding counting numbers. Okay, so that product will be equal to 5,040. Your calculator should have that. So everybody has a different calculator, but I'm just showing you the one in the computer. So 7 factorial is going to be, you see the factorial symbol somewhere. Yeah, you see the factorial symbol as N factorial. So 7 factorial is going to be 5,040. Or you want to do, let's say, 10 factorial. There it is. Barbie. Compute 6 minus 3 factorial. The order of operations is still important. We're first going to simplify whatever is inside parentheses and then multiply the numbers. So a factorial is still a multiplication. Order of operations, let's do parentheses first. 6 minus 3 is 3. And 3 factorial is 3 times 2 times 1, which is equal to 6. Parsing, 8 factorial over 4 factorial. You can always put this in a calculator, but another way you can do this, if you have 8 factorial over 4 factorial, we can eliminate this denominator, because 8 is going to be 8 times 7 times 6 times 5, and the rest is 4 factorial. So we can cancel the 4 factorial and end up with 8 times 6, or 8 times 7 times 6 times 5. So 8 factorial over 4 factorial is going to be 1,680. On a calculator, you can still do that. Using grouping symbols, that's going to be 8 factorial divided by 4 factorial. Or maybe I didn't need the extra parentheses. But 8 factorial over 4 factorial is 1,680. In part D, when we do combinations, we're going to see things like this. Like 9 factorial over 5 factorial times 4 factorial. And we can do the trick that we did in part C. For now, we have 5 factorial and 4 factorial, where 9 is 9 times 8 times 7 times 6. And I'm going to write the rest as 5 factorial so we can simplify some of the terms. We have 9, 8, 7, and 6 divided by 4 factorial is 4 times 3 times 2 times 1. Okay, so 8 over 4, that's 2 over 1. 9 over 3 is 3 over 1. And 6 over 2 is 3 over 1. And finally, this quotient of factorial simplifies as 3 times 2 times 7 times 3. 3 times 2 times 7 times 3 is 126. Some calculators have a formula directly for that. So I don't know what calculator you have, but yeah, you can you can figure that out. You can look for videos or you can look for tutorials to of how to find factorials or combinations or permutations with one button. Okay, so back to example 1. In example 1, we could have computed we found the number of permutations of 7 objects taken 3 at a time. And initially we found as a 7 times 6 times 5. So that's going to be the same as 7 factorial over 7 minus 3 factorial, where 7 minus 3 is 4 factorial. And let's repeat this trick. 7, 6, 5, 4 factorial over 4 factorial. The 4 factorials cancel out, and we ended up with 7 times 6 times 5. Okay, so now I can give you the formula for computing the number of permutations. That's on page 240. The number of permutations of an object taken r at a time is n factorial divided by n minus r factorial. So a couple of examples, I'm just making this up. You can use any formula you want. I mean, you can find that by using this formula with the factorials or by using the fundamental counting principle like I did initially. Okay, so let's find the number of permutations of 8 objects taken 5 at a time. So with the permutation notation, this is P of 8, 5. You can put it directly in the calculator. As I told you, some calculators even have a button that lets you do this. So depending on the calculator, let's write a note in red. On a calculator, you're going to have something like this, like you're going to have a button NPR. And that would be something like 5 NPR 5 or 8 NPR 5. But I don't know what type of calculator you have. So I'm going to finish this problem. That's going to be 8 factorial over 8 minus 5 factorial. So this is 8 factorial over 3 factorial. Or we have 8, 7, 6, 5, 4, and 3 factorial. In that product, this is 8 times 7 times okay, 8, 7, 6. So I need to delete that. Okay, so that's against 8, 7, 6, 5, and 4. So that's 6,720. Or you could have done simply 8 factorial over 3 factorial. You could have done that too. And it's the same answer. Okay, so that was part A. Part B. Let's find the number of permutations of 487 objects taken 3 at a time. Now, if you try to put this directly in a calculator, you're going to see an error because this number is too large. So this is 487 factorial divided by 487 minus 400, let's see, 487 minus 3 factorial. So that's 487 factorial over 484 factorial. And this one, this is 487 times 486 times 485 times 484 factorial. We can now cancel that. okay? And we have so far 487 times 486 times 485. So that's going to be a big number. This is 114,790,770. So some calculators will show you an error due to overflow because the numbers are too large. So if we try that, well, actually, this one is going to do it. Yeah, this one will do it. Okay, yeah, so this one did it. So it really depends on the calculator. Okay, so that was regarding permutations. The title of this section is permutations and combinations, so now we'll see combinations. So in a combination, order doesn't matter. In both permutations and combinations, we are finding we are well, or they both involve different objects, but in permutations the order matters, and in combination doesn't matter. So if we choose our objects from a set of n objects, we say that we are forming a combination of n objects taken r at a time. The notation C of n comma r denotes the number of combinations and of such combinations. So the formula for the number of combinations is going to be n factorial divided by r factorial over n minus r factorial. So a few notes, some notes. In a combination, order is not important. In a permutation, order is important. Okay, like some examples. Let's say pin 4-digit pin number. Let's call this 4-digit pin numbers are permutations. You know that 1, 5, 6, 3 is not the same as 6, 6, 5, 3, 1 or 5, 3, 1, 6. On the other hand, playing the lottery involves combinations. As long as you have the winning set of numbers, it doesn't matter the order in which you selected the numbers. So all you need is the winning set of numbers, regardless of the orders in which they were chosen. Okay, so summarizing, the number of permutations of n objects taken r at a time is n factorial over n minus r factorial. And the number of combinations of n objects taken r at a time is n factorial divided by r factorial times n minus r factorial. And whether the problem involves combinations or permutations, that really depends on the context. Okay, examples of combinations. This is example 4. On page, same page, 641. How many groups of 3 pictures from a set of 5 can you select to make a custom collage for your Facebook cover? So all you want are 3 different pictures. So you just want 3 different pictures. Doesn't matter the order in which you will arrange the pictures or the order in which you selected them. So order is not important. You just want to know the number of combinations of 5 objects taken 3 at a time. According to the formula, this is going to be 5 factorial divided by 3 factorial, and 5 minus 3 is 2 factorial. That is going to be 5 times 4 times 3 factorial, and then 3 factorial, 2 factorial. So the 3 factorials cancel out, and 2 factorial is equal to 2. So 4 over 2 simplifies as 2 and 1. Okay, so you have 10 groups. 10 groups of 3 pictures. In B, in how many ways can you select a 4-person committee from a set of 10 people? So again, you just want 4 different people. As long as they are not taking different positions, like one is let's say one is a president, another vice president, a treasurer, and a vocal. Well, in that case, the order would matter, because if you're only selecting 4 different people, the order is not important. So we're looking for the combinations of 10 people taking 4 at a time. This 10 factorial over 4 factorial times 6 factorial. Okay, so 10 factorial, we can rewrite this as 10, 9, 8, 7, 6. So the 6 factorials cancel out. And next we have 10, 9, 8, 7 over 4, 3, 2, 1. Okay, we can simplify 10 over 2 as 5 over 1. 9 over 3 as 3 over 1. And 8 over 4 as 2 over 1. That is 5, 3, 2, 7 times 7. And that's 210. So you have 210 ways to select a four-person committee, as long as you have 4 different people and they don't occupy or they don't take different charges. Now, most of the time, it's not going to be that evident, and all I can tell you is that from the context, you can determine whether you should find combinations or permutations. Okay, let's look at number 32. These are on page 648. Okay, producers wish to interview 6 actors on 6 different days to replace the actor who plays the Phantom in Broadway's longest running play, The Phantom of the Opera. So they are going to interview 6 actors on 6 different days. Okay, so we are going to, or they are going to choose 6 actors. One per day. So the order in which they interview the actors is important. Let's suppose we have day 1, day 2, day 3, day 4, day 5, and day 6. Yeah, so I'm not even using the formula. I'm just using a slot diagram. Okay, so on the first day, they have 6 actors to select from. Once they interview the first actor on the first day, on the second day, there are 5 actors remaining. On the third day, there are 4 left. On the fourth day, there are 3 remaining, then 2, then 1. Well, at the end, what we did was find the number of permutations of 6 actors, taken 6, selecting 6 at a time. So we selected the actors according to the number of, according to the day in which the actor is going to be interviewed. From the formula, this is 6 factorial over 6 minus 6 factorial. Well, 6 minus 6 is 0, but actually 0 factorial is 1. So 6 factorial is 720. 0 factorial is 1. So they can schedule the interviews in 720 different ways. So the order was important, and the order was determined by day. So order is important, and it is determined by day. Now, number 34. Annette has rented a summer house for next semester. She wants to select 4 roommates from a group of 6 friends. Okay, so all she wants are 5 different friends, 4 different friends. from a group of 6, she's going to select 4. So the order is not important as long as she has 4 different people. So this one, the order is not important. The order in which she selected her friends is not important, so we're going to find the number of combinations of 6 objects taken 4 at a time. And that is 6 factorial divided by 4 factorial times 2 factorial. So that's 6 times 5 times 4 factorial divided by 4 factorial, and 2 factorial is 2. Okay, 6 times 5 is 30 over 2, so that is 50. Okay, so she can select her 4 roommates in 15 different ways. Yeah, I'm trying to rotate this. Okay, I'll have to do that. Okay, there it is. So she can select her roommates in 15 different ways. Next example, we have 2 situations that look very similar, but one involves combinations and the other one involves permutations. So we're doing number 39 and 40. Okay, number 39, 10 magazines are competing for 3 identical awards for excellence in journalism. No magazine can receive more than 1 award. And in number 40, the awards are all different. So 10 magazines are still competing for 3 awards, but they are all different. So no magazine can receive more than 1 award. So in number 39, number is not important. Order is not important. They just want to choose 3 different magazines to give them to give each identical awards. So they can choose in. So it can happen in C of 10, 3 different ways. But the combinations of 10 elements taken 3 at a time is going to be 10 factorial divided by 3 factorial times 7 factorial. That is 10 times 9 times 8 times 7 factorial. And then 3 factorial is 6. We can cancel the 7 factorial. And we can do something else. So yes, 9, let's see. Well, I'm going to do this. I'm not going to keep it as 6. I'm going to keep it as 3 times 2. So the 9 and the 3 simplify as 3 and 1. And the 10 and the 2 simplify as 5 and 1. So this is 5 times 3 times 8. Or 120 ways. In number 40, now assume that the awards are all different and no magazine can receive more than one award. Okay, so number 40, the order is important, and I'll tell you why. Okay, let's suppose that the awards are, let's say the awards are the best magazine, the most original, and let's suppose the best new magazine. So you have 3 magazines, let's call them A, B, and C. So you have 3 different magazines, but the same 3 magazines may receive the award in different orders, like BAC or CBA. Yeah, so the order is important because the same 3, essentially, the awards represent the order. The same 3 magazines may receive different awards or may receive the awards in different order. So we are looking for the number of permutations of 10 objects taken 3 at a time. So if you want to use the formula with the factorial or just use the fundamental counting principle, it's up to you. The permutations formula is 10 factorial over 10 minus 3 factorial. So that is 10, 9, 8, 7 factorial over 7 factorial. And 10 times 9 times 8 is going to be 720. So they can receive the awards in 720 ways. And the last 2 examples are about combining counting methods. Okay, so that's the last part. So I'm going back to the book just to read 1 paragraph. One more. Yeah, so far we have done permutations and combinations, but in the last section we did the fundamental counting principle. So in some situations, we must combine several counting methods to arrive at an answer. A problem may involve combinations or permutation. I mean, can involve both permutations and combinations, or you may need a fundamental counting principle with combinations or with permutations. Okay, so next, I have 2 more examples. The next one is still on page 648. That's number 56. So in this one, we need combinations and the fundamental counting principle. Nicetown is forming a committee to investigate ways to improve public safety in the town. The committee will consist of 3 representatives from a 7-member town council, 2 members of a 5-person citizens advisory board, and 3 of the 11 police officers of the force. In how many ways can the committee be formed? So we're going to use, okay, for the town council, they want to select 3 representatives, and that's all they need. They don't want them to take on different positions. So that's going to be combinations of 7-3. Then 2 members of a 5-person citizens advisory board. So that's combinations of 5-2. And 3 of the 11 police officers on the force. Okay, we are going to use the fundamental counting principle. In how many ways can the committee be formed? The 8-person committee be formed? We need to use the fundamental counting principle. To find the number of ways that the committee can be formed. So it's going to be the number of ways to select the 3 people from the town council, the number of ways to select the 2 people from the advisory board, from the citizens advisory board, and the number of ways to select 3 police officers from the force. Okay, so combinations of 7-3. This is 7 factorial over 3 factorial times 4 factorial. So I'm just going to put this in a calculator. So this is 7 factorial divided by 3 factorial times 4 factorial. And that's 35. Then combinations of 5 elements taken 2 at a time. So this is 5 factorial. Okay, so let's write. Okay, so I didn't write this. But this is 5 factorial over 2 factorial times 3 factorial. We actually did this in one of the previous examples. This is 5 factorial divided by 2 factorial times 3 factorial. Okay, so that is 10. And combinations of 11 elements taken 3 at a time, that's going to be 11 factorial divided by 3 factorial, and 11 minus 3 is 8. Okay, so that's 11 factorial divided by 3 factorial times 8 factorial. So that's 165. Okay, so this ended up being 35 times 10 times 165. And after multiplying the numbers, this is 57,750 ways. Okay, so they can select so the committee can be formed in this number of ways. So in this example, we use combinations and the fundamental counting principle. And the last one will involve combinations, permutations, and the fundamental counting principle. This is the last example to finish the section on combinations and permutations. That's number 63. Okay, the students in the 12-member Advanced Communications Design class at Center City Community College are submitting a project to a national competition. They must select a 4-member team to attend the competition. The team must have a team leader and a main presenter. The other 2 members have no particularly defined roles. In how many different ways can this team be formed? Okay, so again, this team must have a team leader. So there's going to be 1 leader, 1 main presenter, and 2 members with no particularly defined roles. Okay, so let's say that they first select the leader and main presenter. And I'm doing that, well, I'm doing it that way because that would be the natural thing to do. Suppose they first select the leader and main presenter. And they can select that in, they have 12 members, and they are going to select 2. 1 is going to be the leader and the main presenter. So the number of ways to select them is going to be permutations of 12 too. The order matters because they can select the 2 people, but interchange the roles. So the same 2 people may interchange roles. That's why the order matters. And the other 2, suppose they first select the leader and main presenter, and then they select the other 2. Okay, so there are 10 members left, and they must select 2. So at the end, permutations of 12 elements taken 2 at a time, that's going to be, I'm just going to go ahead and use the fundamental counting principle. 12 times 11, this is 132. And then combinations of 10 elements taken 2 at a time, that's going to be 10 factorial, 2 factorial, 8 factorial. So that's 10, 9, 8 factorial, 2 factorial is 2. So this 2 cancel out. And then 10 times 9 is 90. 90 over 2 is 45. Okay, so they can select the committee. So the committee can be selected in, they first selected the leader and main presenter, and then they selected the other 2 members in this number of ways. Okay, so that's 132 times 45. And 132 times 45 is going to be 5,940 ways. And I did it in this order because that's probably the more natural way to do things. So first select the leader and main presenter, and then select the other 2. But if for some reason they selected the 2 members with no particularly defined roles, that would be combinations of 12 too. And once they select the 2 members with no defined roles, they select the leader and main presenter from the 10 remaining. The answer is still going to be 5,940. Okay. So this is it. This is the end of chapter 12. Thank you for listening.